This conference will now be recorded.
Okay, so exactly your permutations and combinations are counting methods. All right, so first we'll try to approach the basic counting methods and try to pick up few examples which are not the part of your book indeed, but they will help you in having quite mature approach towards permutations and then combinations, and before that the factorial function, because you can see in the beginning of your book they have just introduced factorial function. Why you use factorial function, what is the reason behind that, what exactly the significance of your factorial function, they haven't mentioned anything here. Okay, so this thing real it can generate a kind of contribution or confoundedness in the students, and why we are using, what is the reason behind. Okay, so for this purpose we just try to approach to our counting methods basic few examples. Okay, because solving the questions is quite easy. You just pick up the formulas, you insert the values, you will get the answer, and it is very correct from the back of the book, and people get happy that yes, we are getting expert in handling the counting methods. But basically behind the curtain they haven't understood the real concept. Okay, so if you don't understand the concept, you won't be able to apply permutations and combination techniques in your professional statistical projects if you just move to your in your professional life, right? So here, for example, if I just pick up that there's a person who is having three pants and two shirts, for example, right? Then in how many ways he can wear these pants and shirts in some nice combinations, okay, in some nice pairing, right? So in how many ways he can wear them. All right, so if I just try to make here that these are the three pants. Okay, if I pick up my pant one, and with this pant I can wear shirt number one and shirt number two. These are this one and two way. And then with pant number two you can wear these two shirts, this is third and fourth way. And with the third pant you can make a combination like this, so this is the fifth way and sixth way. So actually you're having six nice different pairings, unique pairings. Okay, it is a distinct pair, none of them are getting repeated, you can see, right? So there are six pairs which are distinct in which he can enjoy these wearings, right? So this is the way, this is what you say counting technique in short interval of time. Okay, we just made a combination within no time like this. Now this is a crude way of doing. Now if I pick up one more example and I just say that there are four digits, one, two, three, four. Okay, and out of the from these four digits, how many three digits, you need to make three digits numbers. Okay, uh, in such a way that none of the digits should be repeated. Okay, you have to make three digits numbers such that none of the digits, none of them are going to be repeated. Okay, they are non-repetitive. Okay, now you just keep in mind that these are the numbers which are so provided to you. Okay, you have to make three digits or a hundred value number. Okay, so at the first position you can select any of these four numbers you want. So you have four unique choices. Okay, you can pick up any of these numbers out of these four. Now, once you have selected a number from these four, now you're having three choices left because you cannot repeat the number. So for the second position, you have three choices, right? Now, how many numbers are so left? You're having only two numbers left that you can place at the last position. So you're having only two choices now. Okay. So here, in overall sense, you just multiply all the possible choices and you just write down that 24. You're having 24 unique ways to maintain three-digit numbers in such a way that none of them are getting repeated. Okay, that's it. Now, in the same manner, if I just make a modification in the same question, I just say that this time you are asked to make three digits number, and you have facility that you can repeat the numbers, okay, at these three positions. So if there is no restriction of repetition, all right, you can repeat the numbers. Now, in this way, out of these four numbers, at the first position, you have four choices. You can easily repeat the numbers. So for the second position, again, you're having four choices. Okay. And similarly, for the third position, again, you're having four choices because you can repeat. So in this manner, you are having 4 into 4 into 4, that is 4 cube ways, that is 64 ways in which you can form three-digit numbers. So you can make 64 three-digit numbers from this so provided set, okay, in which the digits are getting repeated. All right. Now, if I just ask you, you can orally answer me. If I just ask you that I'm going to provide you a set of numbers, not a set of numbers. I'm going to provide you five alphabets. Okay, A, B, C, D, and E. Okay, and I ask you that you need to provide and you need to tell me that how many ways I can make a word involving all five letters without repetition. Okay, so I need to make a word involving all these five letters in such a way that these letters must not be repeated. Okay, all the letters must be unique. Okay, so how you're going to answer me? How many ways?
5 factorial,
Yes. So why you're calling it 5 factorial? What's the reason behind this?
because they told us we can use the 5 letters, but in any way, as long as they don't repeat. So the factorial will show us like how many options we have, how many possibilities there is.
And behind this factorial concept, the reason is that for the first position you have 5 choices. Now one is fixed. You have 4 choices left. So for the second position you have 4 choices. Now two are fixed. Three are so provided to you. Your third choice. At the third position you have 3 choices. Similarly, it keeps on decreasing till you reach the final one. So this is giving you a touch of factorial. Okay, so this is giving you 5 into 4 into 3 into 2 into 1, which is representing a factorial function. That's why you write factorial. Okay, so this only factorial concept means 5 factorial. It is going to be used only if I just say that you are going to form a letter, a word which is involving all the letters which are so provided to you. Okay, these are n number of letters, and this word is made up of all these provided letters. That's why n factorial is the answer. Now, if I ask you to, out of these five letters, form a four place word, okay, four letters word, which is containing the letters which are not going to be repeated. And this way, here, the factorial concept is not going to be applied because now you're having 4, 5, 4, 3, 2. That's it. So this is not satisfying the factorial. If I just ask you, write three letter word, Out of these A, B, C, D, E, which is not going to be repeated, then 5, 4, 3. Here the factorial is not applied. Okay. So factorial is applied only if all the options given in the major set is getting used here. Okay. If they're all getting consumed, then you can use n factorial, otherwise not. Now, if I ask you in the same question that I am going to make a word involving all these 5 letters and they can be repeated, how many ways I'm going to have in this way now? 5, 5, 5, 5, 5. Because at every place I'm having 5, 5 choices because I can repeat the letters, right? So in this way, you're having 5 in power 5. That is 625 into 5. So whatever the answer is, you're having that number of ways. All right. So this thing depicts that if you're having n number of objects, you're having n objects. Okay. And from these n objects, I ask you to pick up r number of objects. Okay. Select r objects. Okay. And then you have to make number of possible ways through which you can make arrangements from these r objects such that r is uh, you can repeat the numbers or you can repeat the objects in making those arrangements. Okay, you can repeat. So in that way, what you're going to do, you have r number of objects. For example, r is 3 and n is 5. Okay, it could be 5 letters, could be 5 numbers, whatever it is. Okay, you can repeat. Okay, in the combination, in this arrangement, r can be repeated. Okay, so there's a repetition involved. So you have 5 choices here, then 5 choices again here, then 5 choices again here. So it is 5 power 3 number of ways that you can make arrangements. So this thing depicts, if I try to generalize, it is n power r. Okay, so if you have n number of objects, and from n number of objects you need to select r objects, making such kind of arrangements such that the objects can be repeated. So in that way, n power r ways you are having, or n power r permutations you are having to make such kind of arrangements. Okay, so this is one of the case that we study in our permutations. Okay, it's case number 1. Now, if I just ask you, and before asking, I need to put one example. Now I say that I'm having, for example, 5 letters: A, C, I, U, O. All right. From these 5 unique letters, you see all the n values are unique. I'm having n value 5 and they are all unique. Keep this thing in mind. All right. Now from these unique values of n, you need to pick up 3 letters. Okay. So here R is 3 in such a way that alphabets or letters must not be repeated. Okay. There is a non-repetition involved. How many ways you can make a word involving 3 letters out of these, involving no repetition. So here you're having 4 choices, then 5 choices, then you're having 4 choices, then you're having 3 choices. So in results, you're having 5 into 4 into 3, that is 60. Yeah, here you're having 60 ways through which you can form 3 letters word, so that is containing no repetitive letters. If I just try to transform this 60 like this, I can write my 60 as 5 into 4 into 3 into 2 into 1 upon 2 into 1. You might be thinking why she's doing like this. This is what? This is your 5 factorial. I can write 5 factorial like this or like this. I have ways to represent, right? And this is 2 factorial. All right. So now I can express my 2 factorial like this. 5 factorial upon 5 minus 3 whole factorial. This is giving me 2 factorial, am I right? Here in this question, my n was 5 and my r was 3. Okay, so it is n is there. 5 is n and r was 3. So P permutation R can be written like this, and this formula is used when you have been given n unique objects. It could be letters, could be numbers, whatever it is. And from these n unique objects, you are asked to pick up any R objects and form the arrangements in such a way that those R objects must be all unique. They must not be repeated. Okay. So this is the case where you use this formula. So this is your case number 2. Okay, you can write these cases in your notebook somewhere. These are the 2 cases that I've discussed up till now. Okay. Now what is my third case? If I just say that if there are n objects where p objects are getting repeated in that n. Okay. For example, if I just say I'm having 3 balls, out of which 2 are red, one is green or blue, whatever. The third one is the different color. It is having different color. So here my n is 3. Okay, I'm having 3 objects in the set. And out of these 3 objects, R or red ball is getting repeated twice. Okay, so here my P or my R, whatever you want to represent, it is repeated twice like this. Now, I ask you to make combinations of these 3 balls, okay, in such a way that all these balls are getting involved. Okay, make a combination of 3, make arrangements of 3. So I just say red ball 1, red ball 2, green ball. This is one combination, this is one arrangement. And then red ball 1, green ball, and then red ball. Okay. Then I just say green ball, red ball 1, red ball 2. Now if I just swap these red balls here and there, do you think they are going to bring change in this representation? Of course not. Okay, they are going to look same. All right. So in total, I'm having 6 arrangements. I'm not going to use combinations here. This is 6 ways, crudely, but you see out of these 6 ways, 3 ways are similar to the first 3 set of ways, right? So in reality, I'm having 3 major ways through which I can make the set of these 3 balls. Okay, so how I'm going to do my exact ways is 3. How I'm going to manage this? If I just say that there are 6 balls, so I can write 3 factorial. It is getting divided by 2 factorial. Okay, if I try to solve this, because you see here 2.1, so I'm having 3 actual ways. Am I right? So you see, what is your 3? 3 was your n. What is your 2? 2 is the number of times a certain object in the set of n is getting repeated. So this is p factorial. Okay. So whenever you're having a case that you have been provided n objects where p objects are getting same, then how you're going to find the total permutations or total way of making arrangements, it is n factorial upon p factorial. If I further try to generalize this, if I'm having n number of objects out of which few objects are getting repeated p times, few other objects are getting repeated 2 times, few other objects are getting repeated 4 times, like that. So what is going to be the number of possible ways or total number of permutations? I just say P, R, and T. They're getting repeated like this. Then the total number of permutations will be expressed like this. Total number of permutations will be n factorial upon p factorial into r factorial into t factorial. Okay, if I'm having, for example, 10 balls, and out of 10 balls, I'm having 3 red balls, 2 green balls, 4 blue balls, like that. They're getting repeated. So those number of repetition of those set of balls is going to be written in the denominator in the form of a product of factorials. Okay, it's like that. So this was your case number 3, the major case. Clear? The 3 major cases that we have studied in the permutations that we are going to apply in our exercises, okay, or in the topical past paper questions. Related to this case number 3, I'm going to place here an example. Okay, now I just say that I'm having a word. Okay, I just say that I'm having a word, for example, statistics. All right. I just write statistics here. Statistics. All right. Now, I ask you that in how many possible ways you can write this word statistics. Okay. In how many unique possible ways. Okay. So unique possible ways means in how many permutations you are having through which you can write the statistics. I mean, I can write S and S first, then I can write T's at the positions, then I can write A's. Are you getting me? Or sometimes I can write everything in a traditional way. This is one way of doing. This is the way of doing. Okay, this is another way. Then you can write T's first, then you can write S all of them. So you see, you how many ways you can write this word? That's what they're asking. Okay. So what you need to do, just count that how many total numbers, how many total letters you're having here. Okay, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is it. And then how many times S is getting repeated? You just say S is getting repeated 1, 2, 3. How many times T is getting repeated? It is also getting repeated 3 times. Okay. How many times you're having A? A is coming just once. How many times you're having I? I is occurring 2 times. I can say 1 and 2. How many times you're having C? C is occurring just once. Alright. So you see, this is the time number of repetition. This could be P, it could be R, it could be D. That's it. So you see the number of possible permutations is going to be what? It's going to be total number of ways or total number of possible permutations. Whatever you want to write, you can write. So this is what? N factorial upon p factorial into r factorial into t factorial. That's what you're going to do. This is 10 factorial upon 3 factorial, 3 factorial, 2 factorial. There's no need to write 1 factorial. It's understood. Okay. So there's no need to mention. We only write those values which are greater than 1. Okay. So you can write n factorial upon 3 factorial whole square upon 2 factorial. Now you can use a calculator. You can get the value. Okay. So it's going to be, after solving, 50400. Okay, so 50,400 ways you're having in writing this letter, in the writing this word statistics. Okay, so in 50,400 unique ways you're having where you can swap the letters, you can write T first and then S and then C, whatever you want at the unique positions. Okay, this is the way to do. Now if I just place one extremely uh, interesting and important question, if I just write here that I'm having whole numbers, if I'm just having a set of all whole numbers starting from 0 to 9, okay, like that. And so this thing is telling me that I'm having n number of digits, n equals to 10 digits. Okay. You can also notice here they are all unique. Okay, they're not getting repeated. Keep the cases in your mind that we are going to apply here. Now they're asking it how many ways we can make numbers involving 8 digits, and here repetition is not involved. Okay, so you're having R value 8 here, repetition is not involved, n is also unique. Okay, so it is case number 2, I'm telling you. But we are going to solve this using permutation as well as counting technique in through counting method as well, and also through permutations. And we are going to do through both ways so that you can understand that how what kind of relationship you're having between permutations and the counting technique. Okay, so I just say that I'm having a number involving 8 digits. Okay, involving 8 digits means first first digit must not start from 0, because if it starts from 0, then you are going to have a number which is containing 7 digits. Because you see, if I write a number like this, 1372, then basically it is 172, right, in significant figures. So you are not going to start your number from 0. If they have just specified that it is an 8-digit number, so it should be like this. Okay, 0 must be on some other place starting from the second up to 8th position. It can be placed at these positions but not at the first position. So here I'm having, for the first position, I'm having 9 choices from here to here excluding 0. So I'm having 9 choices here. I can pick up any number from 1 to 9 over here at the first position. Okay, now at the second position you can use 0. Am I right? And they have just said that numbers are not going to be repeated. So this is non-repetitive position, non-repetitive case. Okay. So if you have selected, for example, if you have selected 1 here, now in all these remaining positions, you can't use 1. So now how many choices you are having? You're having 0 and the remaining numbers from 2 to 9. So overall, you're having 9 choices still. So for the second position, you're still having 9 choices. Okay. Now, for example, if I've selected 0, now I'm having 8 choices. And now you just keep on moving accordingly. Okay. Now you're having 7 choices, then 6 choices, then 5 choices, then 4, and then 3. Okay. So in how many ways you can organize numbers involving 8 digits in a non-repetitive order? 9 into 9 into 8 into 7 into 6 into 5 into 4 into 3. Okay, whatever the calculator is going to tell you the value, you're going to write that number of ways you can organize a number involving 8 digits. Okay, Now, in the same case, in the same question, if I just make one modification and I just say that write down 8-digit number, you have freedom, you can repeat the numbers now here. And make sure they are 8-digit numbers. So it's still at the first position, I can't write 0. Okay, so for the first position, I'm having 9 choices. I'm having 9 choices because I can't write 0 here. So from 1 to 9, I can write any number over here. Now, from the second up to last positions, I can write any number from 0 to 9. I have 10 choices. I can do repetition. So again, I'm having 10 choices, 10 choices, 10 choices, 10 choices, 10 and 10. So in how many number of ways I can make this combination? 9 into 10 power 7. So this is 9. Okay, this number of ways you're having. I hope it's clear. So you see, this is the permutation that helps you in organizing millions and millions and millions of mobile numbers, millions and millions and millions of your ATM card numbers. They are all unique, they are all different. So permutation is the method of organizing such kind of numbers and combinations. Now, if I just say that uh, I'm having, for example, a set of letters like this, and now you see n are not unique, they are getting repeated here. Okay, so n is not distinct. Okay, the objects are not distinct here. And I ask you, I'm having total value 10 here, and I ask you to write the total permutations of writing a letter, writing a word, sorry, involving all these 10 letters. Okay, and what is going to be the total number of ways, total number of ways of writing a word involving these 10 letters. Okay, so here it is, this is the formula that you are going to use. All right, this is 10 factorial upon how many ways b is getting repeated? 2 times. C is getting repeated 3 times, and D is also getting repeated 3 times. So I can write 3 factorial whole square. Then I can solve, and whatever the answer I get, I will just write these are the number of ways through which I can organize the letters and make a word involving all these 10 letters like that. Okay.
I have a question.
Yes. Yes.
This 10 factorial is the total, right?
12 factorial is what?
And 10 factorial is the total, right? It's all the total outcomes.
Yes.
Then why do we divide by the probability we're doing and not by the total outcomes? So why
Yeah,
is it 10 and negative?
I told you that once when we were just trying to understand the formula of this case. I just give you an example of colorful balls, this one, and then I generalized. Okay, at why we divide by p factorial and r factorial and t factorial. Okay, for example, over here I just try to explain this. You see here, I just repeat this now. I picked less number of n in order to understand the concept, and then I can increase number of n once when I generalize my formula. Okay, you see over here in the set of n, I'm having 3 balls, and in these 3 balls, 2 balls are having the same color. Okay, so here p is 2. Clear? One thing is done. Now I ask you to make to arrange these balls in all possible ways. We arranged it now. You can see R1, R2, RG, and R2, R1, RG. These two balls are actually giving you the same appearance. For example, you can understand it over here like this. If this is your red color, okay, there's the two balls, and this is my green. My green is too light. This is it. Okay. Now here, this is my R1, R2, and G. Okay, and this is my R2, R1, and G. Can you see any difference in this combination? Of course not. They are same. They look same. Okay. So similar, same. Those arrangements which look same, which are similar in appearance, you're going to count them just one way. Okay. So actually, these two ways are going to be considered just one way. That's why instead of writing 6 ways, I wrote that there are 3 unique ways of organizing these 3 balls. All right, in arranging all these 3 balls, there are six. There are 3 unique ways instead of 6. Okay, so you are not going to write that it is there are 3 factorial methods. This is wrong. Okay, you're not going to write n factorial number of ways. You will write that there are 3 ways. Now I'm going to generalize the formula. You can write 3 ways can be written as 6 upon 2, right? 6 can be written as 3 factorial. 2 can be written as 2 factorial, right? So what was your 3? 3 was your n in this question. In this question, 3 was your n. What was your 2? 2 was your p. Number of times red is getting repeated. Okay. So the elements which are in the set of n, the number of elements which are getting repeated are going to be written in a factorial form in the denominator in order to get the correct number of ways, correct number of possible permutations. Okay. So in the same manner, if I just include that if I'm having 2 greens and 2 red balls, and how many total number of permutations I'm having this time. So this time you see that red is getting repeated twice, I call it P, and green is getting repeated twice as well, I call it R. I just call it R. Okay. So now you can generalize your formula that number of ways are going to be n factorial upon p factorial into r factorial. Okay, so this time if I'm having a case this, and this time you're having 3 factorial upon 2 factorial into 2 factorial, so actually I'm having 6 upon 4. So this is actually quite absurd case, but I'm just trying to maintain a concept that how we have derived the formula here. Okay, so this is the reason that why you divide with your p factorial, r factorial, and t factorial. This is the way to get the correct number of combinations here. Okay, if you're having unique values of n, if you're having a, b, c, d, e, if a case is this, and I ask you, and they are actually 5, and they're all unique. There is no repetition in your set n. Okay. Now from these unique letters, I need you to form a word involving 5 letters in such a way that all of them must not be getting repeated. None of the words should be repeated. Okay, all of them should be unique. If I use A here, I can't use A in these remaining 4 positions. I'm no more allowed. Okay, now in this case, you are going to write down that there are n factorial or 5 factorial, means 5 into 4 into 3 into 2 into 1. This number of ways I'm having in writing the word having 5 letters, and they are all unique. In case of uniqueness, you are going to use just n factorial. Make sure that your n and r values are same and n is unique. First condition, second condition, and the third condition is that none of the letters must be repeated. None of the objects are going to be repeated. In that case, n factorial is going to represent the number of possible number of possible permutations. Okay, but if your n is getting repeated inside somewhere, and you're asked to find out the total number of permutations, you're going to use this formula. Okay, because there are going to be many arrangements inside which are giving you the same appearance like this. So we need to avoid that. That's why this formula is generated. Any questions? Is there any still confusion?
No.
If I ask you one question, then we'll approach the exercise. I'm having first 9 natural numbers. Okay, means my n is 9. You can see that they are all unique. None of them are getting repeated. Okay, from these 9 digits, I need you to form a number involving only 3 digits. Okay, so here r is 3. Okay, and I ask you that make sure that none of these digits are going to be repeated. All right, so what is going to be your method of doing? You have two methods, counting method and permutation method. Okay, they are not going to be repeated, so non-repetitive. All right, so whenever you have n value with unique n objects which are all unique, you are asked to find out number of ways having some r value out of this, such that none of the objects are going to be repetitive. You're going to use this formula. Am I right? Why we are using this formula? I repeat. Here you're having 9 choices. For example, you have selected 2 here. Now in the remaining 2 positions, you can't use 2. You have 8 choices for the second position. For example, you have selected 4. Now you are having 7 choices left. Okay, so in total, you're having 9 into 8 into 7, that is 504. All right, this is counting technique method. Another method is your permutation method, and it is going to be written like this: P permutation 3. So it is 9 factorial upon 9 minus 3 factorial. It is also going to give you 504. It is 9 factorial upon 6 factorial. I can break it up. It's 9 into 8 into 7, and then 6 factorial I can write as it is upon 6 factorial. You cancel it, you're having same 9 into 8 into 7, that is 504. Clear? We have 2 ways of doing this. All right. If I ask you that make 3-digit number and you have freedom, you can repeat these numbers, n are all unique, what is going to be the method? Which case you're going to follow? You have 9 choices here, 9 choices here, 9 choices here. So 9 power 3 is going to be your answer. So this is n power r, case number 1. Okay, that's it. Similarly, if I give you 1113, one more one. Okay, how many n's you're having? 5, and they are not unique. Okay, they are getting repeated here, where 1 is getting repeated 4 times. Here p is 4. I ask you to generate here a 5-digit number. Okay, what is going to be the formula to to find out the total number of permutations. 5-digit number you need to form. How many ways you can form? N factorial upon p factorial. Are you getting that? This is going to be 5 factorial upon 4 factorial. So it is going to be 5 times 4 factorial upon 4 factorial. This get cancelled. You're having 5 ways to write down 5-digit number. Okay, it could be 11113. This is one way. 31111 second way. 13111 third, and if I just write 113111 like that. I wrote one extra. This is it. And 11131. So these are all 5 unique ways through which you can form a 5-digit number. Okay. Remaining combinations, if I pick up n factorial 5, it was 120. So from 120, if I subtract this, 115 ways are actually going to give you the same face of numbers. So that's why they're not going to be counted. Okay, so that's it. I just saw your first exercise here, uh, and it was quite baby type. So if you need my help here in any of these questions, I'm here. Otherwise, we'll jump to 5B. That was the basic exercise actually.
Just let's skip it.
Okay. Okay, now here. In how many ways can the 6 letters, these are the letters, be arranged in a row? Okay, so I need to form, or I need to organize all these 6 letters in different ways in the same row, and
Just keep
they're all
left one.
unique. 6 factorial, 720 ways they are. Yes, that's it. Now, question number 2, from a standard deck of 52 playing cards. Okay, find how many ways there are of arranging them in a row. Uh, in part A, they just say all 52 cards you need to arrange in a row. What is going to be n factorial? Okay, you can't just say n factorial over here. Okay, because there are 4 kings and some spades. They are all repeated actually. I mean, kings are getting repeated, because I do not know exactly what are the arrangements in 52 cards. There are many cards which are getting repeated. They look same. So in that case, it is going to be 52 upon number of cards which are getting repeated. Like we are having 4 kings there, and I think 4 queens or 3 queens, something like that. Let me just find it out. I won't do it without having confirmation. Okay, as far as these black first row is concerned, they are all having unique appearance. They are all unique. As far as these kings are concerned, these kings are, though they have same king, but alphabets are different. Okay, and their appearance are also different. They are all J's. These are J's, 4 J's, 4 K's, and 4 Q's. Okay, so you see J's, Q's, I mean they are jockey and king and queens. These are the cards which are getting repeated here. Okay, joker or jockey, whatever they are. So there are 4 jockeys and 4 queens and 4 kings, and rest of the cards they are all unique. Okay, So 52 factorial upon 4 factorial into 4 factorial into 4 factorial, that is going to be the answer as far as I've understood. So it is going to be written like this: 4 factorial into 4 factorial into 4 factorial. So number of ways is going to be 52 factorial upon 4 factorial whole cube. You can solve, you can get the number of ways here. Okay, this is the way how we do this part A. Okay, if all of these parts are going to be unique, if all of them are unique, then it is going to be simple n factorial ways. But here they are getting repeated. Okay, so we are going to use our case 3 formula, which is this. Okay, I hope it's clear. In B, they are just asking what they're asking. And how many ways there are that you can arrange 4 kings. Okay, so you are having 4 kings, and from 4 kings you need to organize 4 kings. Okay, so actually just n factorial, that's it. Okay, so this is 24. In 24 ways you can do this. Okay, and as far as your and how many ways you can arrange 3 diamonds, you can see here this last row. Okay, it is containing 1 2 3 4 5 6 7 8 9 and 10, the last one. We're having 10 diamonds here. Okay, so and in 10 diamonds, the king and queen and jockey, they are representing diamond category. Okay, wait a second, I made a mistake here. You see, in all these rows, these kings are actually representing hearts. This black hearts, red hearts, this red, this what's this? I mean, third flower, black flower, whatever it is, and the diamonds. So actually, they are unique because of their categories. Black hearts, red hearts, they are making them different from each other. If this is not the case, then they are same. But this is my bad that I made a mistake. So here, they are all unique. I'm sorry for this. Actually, I don't play cards. So this is it. So n factorial is going to be the total number of ways because all cards are unique here. Similarly, how many hearts I'm having? In total, I'm having 13 unique hearts, all of them. So I can make 13 factorial, same n factorial formula or npn formula. So there is 13 factorial ways you can make in organizing these diamond cards. So that's how we do. And then question 3, what is this? In how many different ways can the following stand in a line? 2 women. Of course, these 2 women are different. You are different, I am different. Okay, so we can stand in 2 unique ways. 2 factorial unique ways. 2 factorial is 2 actually, right? So here my n is 2, so number of ways, total number of permutations, why I'm calling this permutation, why not combination? Because here order is representing a different appearance. How? I'll just let you know here. It is 2 factorial. There are 2 ways. Now you see, if you are standing at the first position, I'm standing at the second position, we look different. If I stand at the first position, you are standing at the second position, now we are having a different arrangement. So you see, order matters here. That's why those arrangements where order matters, they are called permutations. And those arrangements where order doesn't matter, They are called combinations that we are going to study later. Now, what do you say about three boys? And how many different ways three boys can sit in a row on a bench? Three boys are all unique, of course. They're sitting at three positions on a bench. The first boy sit here. The remaining two positions are for the remaining two boys. Two choices and one choice. Okay, that is 3 into 2 into 1. That is 6. That is actually 3 factorial, which is actually n factorial. That's it. That's your answer. And now, if I just say, let's proceed to your third part. Okay, there are actually 6 men. I just pick up this part. Okay, now 6 men. They're all unique, n factorial. Okay, and how many different ways can the 6 men stand in a line? It's 6 factorial. That's it. 720 ways. 8 adults can stand in a line. All 8 adults are unique. Okay, there are no twins or quadruplets concept there. Okay, if there is a concept, then you're going to use case number 3, n upon n factorial upon p factorial. But here they're all unique. Once they're unique, n factorial is going to represent number of permutations. So 8 factorial will be the answer. It's simple as that. I pick up part C from question number 4. In how many different ways can the following sit in a row on a bench? 4 girls and 3 boys. Okay. All of them are sitting in a same row. Okay. So there is no concept of R here. Everywhere you can see just N. All the N values are occupied. So I'm having girls and boys. They're all unique. Okay. So 4 girls and 3 boys, 7 factorial. All right. Okay. So you see, girls are unique. It could be Anna, it could be Jane, it could be Aisha, whatever it is. Okay. Let's make a different name. I just say Sarah. They're all unique. Okay. Margaret. The 4 are unique, and 3 boys. I just say William. We are having Ali here. We are having Muhammad here. Okay. So they're all unique. Once they are all unique, so they can sit in n factorial ways. Means 7 factorial is going to be the answer. That's it. And now you just talk about your question 5. What this question is asking us to do: 7 cars and X vans can be parked in a line in this much ways. Okay, there are a huge number of ways here. Okay. Find the number of ways in which in which 5 cars and X plus 2 vans can be parked in a lane. Now you see, they are all unique vehicles, and because if I talk about cars, I'm not going to consider them same, because they are going to have different number plates, right? So their number plates is making them unique. Similarly, if I talk about my vans are also unique because of distinct number plates. So I'm having 7 cars and X vans. So total number of vehicles, they are all unique. So N is unique here. Keep this thing in mind. Okay. Question number 5 we are doing. So 7 plus X, this much factorial is actually equals to 3, a huge figure, 399,16800. 399,16800. This number of ways they can be arranged. Okay. And then later they just say that now they are having 5 cars and x plus 2 vans. 5 cars and x plus 2 vans factorial. So actually it is combinedly 7 plus x. So it is representing same number of ways as far as I've understood. This is going to be the answer, nothing else. Okay, but they have just tried to confuse you by just changing number of vehicles. Okay, now they have made 5 cars, 7 vans. Okay, but they are all unique. Once they are all unique, we are using just one formula, that is n factorial. Okay, so total number of vehicles remains same here. Actually, there is no change. So the number of days also doesn't change. That's it. Now, uh, if you talk about your sixth question here, let me just increase the size a little. Okay, now it's better. A woman has 10 children. Whoa. She arranges 11 chairs in a row and sits on the chair in the middle. All right. So it means that on the left side there are 5 chairs, on the right side there are 5 chairs, okay, where the 10 children can sit. If her youngest child sits on the adjacent chair to her left, in how many ways can the remaining children be seated? Now, one child has also taken the position. Now, there are 9 children so left. Okay, so and the seats are also 9. Not the seats. How many seats we're having? Yeah, we're having 9 seats. So you can organize in a way. This is just for understanding that I'm doing. You can use the formula directly. So this is 5, 6, 7, 8, 9, 10, 11. Now over here, mother is sitting. Okay, here you go, the mother. And on the right side, the youngest child. Okay, the 10th child is sitting here. Now we're having how many seats? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 seats are so left, and so do 9 children. Okay, so it is a non-repetitive arrangement, of course. Okay, because the children are not getting repeated, that's why. So you're having 9 factorial ways, actually n factorial. Okay, because now n are 9, there are 9 children. Okay, so this is n factorial. Whatever the n factorial gives you, that is the number of ways. That's going to be the answer. Okay, so what exactly, you just need to understand the theme of the question, and then you are going to decide that in which case of permutation it is fitting. You are going to use that formula. You are going to find the number of ways. Simple as that. Okay, so just keep the cases of permutations in your mind. All right, now the last question of this exercise. A group of n boys can be arranged. N boys, we do not know the exact number, so we just pick up an arbitrary variable n. Okay, n number of boys can be arranged in a line in a certain number of ways. How many number of ways, we do not know. By adding 2 more boys to the group, the number of possible arrangements increases by the factor 420. Okay, find the value of n. Now, let's see. I just say, if I'm having n boys, I can make n factorial ways to arrange them in a row, right? If I'm having n plus 2 boys, I can make n plus 2 factorial ways to arrange them in a row. And they have just said that this number of ways is actually 420 times more than this arrangement. Okay, so I can write that n plus 2 factorial upon n factorial is equals to 420. Before further doing the steps, let me give you a little example. If I just say that I'm having 6 factorial here and 4 factorial here, actually this is 4 plus 2 factorial upon 4 factorial, am I right? That's it. So this is your n plus 2 roughly. Okay. So if I just say that I just write 6 times 5 times 4 factorial upon 4 factorial. So this is going to be cancelled. What I'm having is 6 and 5. So left. Okay. So if this is your n plus 2, this is your n plus 1. Am I right? So once when I cancel it, it's n plus 2 times n plus 1 into n factorial upon n factorial. That's the case actually. Just cancel them. And now you can expand these two nice looking factors, and of course it is going to give me a quadratic equation. So n square plus n plus 2n plus 2. I can shift this 420 here. This is it. So I'm having n squared plus 3n minus 400 equals to 0. You can factorize, use your quadratic formula, get the two values of your n and tell me what they are. Make sure n is representing number of ways. It should be a natural number. Go ahead. Tell me the two values of your n.
Should we solve using n?
You see, these are the two values that we are having here. Is this what you're getting?
It's just now I got 18.5, but I now get the second value.
So you can, what you're going to do, don't round this, don't make it 19, make 18. Okay, because actually it's representing number of ways. So 8.5, 18.5 number of ways doesn't make any sense, and you can't make it 19 according to the rule. You can't make, it's a number theory rule, it's not a statistical rule. Okay, in a practical way, you can't say that 18.5 can be represented as 19 ways. Actually 18.5, before 18.5 you have confidently made 18 unique ways, right? So you're going to pick up 18. This is going to be the answer in your statistics. Okay, uh, because after 18.5 you are unable to make 19 ways, so you are not going to pick up this option here. Okay, it's like that.
So
So
do I
that's
give 18 or just as 18.5?
no, 18.5 number of ways doesn't make any sense. You have to pick up a natural number. Okay, so pick up 18. So there are 18. Wait a second, what was the question? uh, 18 possible values of n. So there are 18 boys. Okay, where we can make a possible arrangement in such a way that 20 boys, number of ways for the 20 boys is going to be 420 times greater than 18 boys combinations, like that. This will be the answer. So I hope it's clear. You can check the answer from the back, what it is going to give us. I can't directly move to the page. Let me just do it here. Say at 251 probably. I was having answers maybe. I'm doing 5B. Yeah. Okay. They have just said 19. Why they have said 19? When in statistics we used to truncate because
Because our teacher told us that like the mark scheme in the book is sometimes like wrong or inaccurate, so it's not always right.
wait a second, we can make a check work here. Okay. uh,
Yeah.
they've just said that if I pick up n value 19 over here, then 19 plus 2 factorial, active calculator, upon 19 factorial, is this is giving you 420. In other words, 21 into
Yeah, man.
20, yeah, it's giving you 420. On the other hand, if we pick up 18 plus 2 means 20 factorial upon 18 factorial, that is going to give me 20 into 19. So it is giving me 380 ways, so it is not satisfying. So that's why we are going to pick up n value 19. This is the reason of selecting. Either we can round or we can truncate. Before taking this decision, do a little check work and then select your value. Okay? Because in number theory we can truncate and round, we can truncate or we can round blindly. Okay, we know that if the decimal value is 5 or greater than 5, we are going to add 1 in the whole part, but if it is less than 5, we are not going to add 1 in the whole part. This is the number theory procedure. But in statistics, actually you are doing some practical life work. Okay, you are making combinations for the practical life work projects like that. So over here you have to be very cautious in finding out the exact number of ways or in finding out the exact number of objects, whatever they're asking. So for that purpose, you have to pick up a check work and then select either you have to round or do you have to truncate. Okay, that's it. We have 7 minutes more. So let's pick up your 5 5C. Let's see how many questions we can cover here. Your 5C, we were on page number 136 or 138. Um, okay, part B. And your next one is, yeah, permutations of n objects with repetition. N factorial upon p factorial. Uh, this is the category which is representing case 3 questions. Okay. Now, case 3 is something that abundantly comes in your exams. Okay. I'm going to pick up here my question number 1. And from here, I'm going to pick up part A and part E, the first part and the last part. So they're asking to find out the number of distinct arrangements of all letters in these words, number of unique arrangements. Okay. Case number 3, n factorial upon p factorial into r into t. This is the formula that we are going to use to find the total number of unique arrangements or unique ways or permutations. That's what we are going to use. Okay. N is actually representing objects which are not distinct. This is the case. Okay. I'm using table. All of the letters over here, they are unique. None of them are getting repeated. So N is 1, 2, 3, 4, 5. Okay. So here P is 1, R is 1, T is 1. So there is no need to represent them in the denominator. Okay, so number of ways is actually n factorial and it is 5 factorial, that is 120. So there are 120 ways over here. In the last part, E. The word is, I'm not going to read this. Uh, HU sounds like an African word. Okay. Okay. Now you're going to see that how many times. Actually, what are the exact number of n here? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 n values 11 here. Now, if I talk about my H is occurring just one time. My U is occurring also just one time. Okay, my L is occurring four times. My A is occurring two times. Okay, my B is occurring one time and O is occurring two times. Okay, those letters which are getting repeated, which are not getting repeated, they are just H and B. No need to write their appearance in the denominator. Okay, so the number of ways are going to be n factorial. So there's 11 factorial upon 4 factorial into 2 factorial into 2 factorial. That's it. This, and this. Okay. Only the repeated alphabets are going to be written in the factorial form in the denominator. To avoid similar looking arrangement, we just do this step. Okay. Now you can you can solve this through your calculator, and you can get the number of ways then. Okay, could be a huge figure, of course. That will be your answer. You can check from the back then. You just go to the back. You can use a calculator, get the value, and then we'll tally. This is going to be the value. Okay, and I hope it's going to be correct. And then I need you to do part D by yourself. Mississippi, a state in your America, North American state it is. Mississippi here. That's it. It's part D.
Just 1 second, I'm doing it.
Mm-hmm.
Yes, I'm getting 11 factorial divided by 4 factorial times 2 factorial times 2 factorial.
So is it giving you this value? 34650. Hmm? Okay. Okay.
Yeah, miss.
Okay, that's too good. Okay, so Let's do question number 2 and then we'll end up the class. Find how many 6-digit numbers can be made from these sets of digits. I'm going to pick up here the part D. Okay. In part D, you're having 2 8s and 4 9s. All right. Total numbers of n is 6. Okay. So here I'm having 2 8s, 4 9s. Okay, you can organize these digits and make a 6-digit number. How many ways you can make them? You see, n is not unique. You're going to use your regular formula. So the number of ways is going to be number of distinct ways for which you can form is 6 factorial upon 2 factorial into 4 factorial. Let's say it is 6 into 5 into 4 factorial upon 2 factorial into 4 factorial. This is giving you 15. There are 15 ways. Okay. Greater is going to be the repeated elements in your set of n values. Less will be the number of ways. Keep this thing in mind. Okay. I need you to do part B.
Um, yeah, I got 20.
Yeah, that's it. Okay, so that's I think we should end up the class over here. Inshallah, on Monday we'll try to continue from where we stopped. Okay.
Okay, miss.
Okay then. Allah Hafiz. Take good care of yourself.
Bye, miss.